Hello friends, my name is Chinmay Deshpande, and in this video lecture we are going to discuss about a topic from power system stability. The name of the topic is effect of fault clearing time on the stability. Let us consider that there is a one synchronous generator which is supplying the power to the infinite bus through a transfer reactance and a transmission line. So this is your infinite bus whose voltage is V equal to 1 per unit, or you can write it as 1 at an angle 0. Here let's say the voltage of the generator is E at an angle delta. Now what we observe here the fault has been takes place at point X. Now if the fault is cleared rapidly, the system will be stable. What is X? X is the point, or X is the fault point which is adjacent to the bus, adjacent to this bus 1. So therefore what happens due to this fault, the voltage at the bus bar is 0 and the power flow will be equal to 0. Means what? Let us assume that instead of having this fault at this point X, almost it is on this bus only. The fault is almost it is on bus only. So if the fault is there on the bus, then the voltage which is associated to that bus will be equal to 0. And if the voltage of that bus bar 1 equal to 0, then but obvious your PE, electrical power, will be equal to 0. So as we have this is the P delta curve. This is P delta curve we have drawn here. It is P which is there, PE or P on y axis. This is delta on x axis. So this is power angle curve, and this will be your delta on basically this is a y axis. Now here we have drawn it in this way. So this is, you treat this as a x axis, this will be the time t, but you have to see this diagram from this direction, because anyway this is a swing curve that we always used to draw, delta on y axis and time t on the x axis. Now let us consider, let us check all the area and all the points. What happens exactly at point A, B, C, D, E, F and G. So we will discuss this one by one. Let us say the PM or PM0 is nothing but it is your initial mechanical input. Now this is the point A. What is to be observed at point A? This is point A. Your PM or PM0 will be equal to, it is intersect at this curve. So PM0 will be equal to what? PE. So therefore what we can say? This is the before fault point or before the occurrence of the fault. At A, PM will be equal to PE, and therefore what happens in that case? Here the speed omega will be equal to omega s only, and rotor angle delta will be equal to delta 0. So that's why here the rotor angle will be equal to delta 0. This is your initial operating point when there is no any fault. Now when the fault occurs at point X, we already discussed that. At point X means what? It is adjacent to bus bar 1. So we will treat this as fault is there on this bus bar only. So what happens? Voltage will be 0, and we know that PE will be equal to what? EV upon X into sine delta. So as voltage will be equal to 0, this term PE will also be equal to 0. So that's why what happens whenever there is a fault, then the curve, the nature of the curve will be, it will be shown like this. Now from A to B what happens? Your value of PE is go on reducing. Value of PE is go on reducing. At point B what happens here? What you observe at point B? At point B, here I will write as, at point B we observe that as voltage equal to 0, PE will be equal to 0, and that electrical characteristic will shift from point A to point B, which is along x-axis. So I will write it here. We know PA will be equal to what? PM minus PE. This PE will be equal to 0. So what your PA will be? PA will only have a value equal to PM, which will be a more positive. That is, it goes into the acceleration area. Due to a large amount of acceleration power, the rotor will start accelerate and the load angle delta will start increasing. So if you observe, the load angle delta will start increasing in this direction along x-axis. Now what happens at point C? This is the point C which is shown here, and here we have written is delta C. Please see it carefully. I will zoom this. This is nothing but your delta C. So what this delta C indicates? When the delta equal to delta C, when your value of load angle delta, I will write it here at point C. At point C, when delta equal to delta C, circuit breaker will operate, circuit breaker opens and the fault is clear. Now once the fault is cleared, the clearing angle delta C will be increased and PE will suddenly jump from point C to point D. What happens here, if the fault is cleared, again it will go to its original state, that is it will go to the point D, which is shown here. It will go to point D. Now what is the value of power at point D? So I will write it here at point D. PE will be equal to Pmax into sine delta C. But here what is the speed of rotor? Still the speed of rotor is greater than synchronous speed. Why? Because when your electrical characteristic shifts from point A to point B, then here there will not be any electrical power. At point B, PE will be 0. So we have only accelerating power will be equal to mechanical power, which is more positive. Large amount of acceleration will be there. So because of acceleration, power is more, the rotor angle delta increases, and but obvious the speed will be greater than synchronous speed. But still at point D, your speed will not be reduced, it will be still greater than omega s. And your operating point will suddenly shift from point C to point D whenever fault is clear. Now what is to be observed after point D? Now here it is shown from point D to point E it is shown. Now if you go for a point E, then I will write it here. What you observe? This is your PE and this will be your PM. This is your PE, this will be PM. So I can write it here as what happens at point E. At point E, PE will be greater than PM. Yes, it is self-explanatory. You can see here in the figure. PE, this is PE, which is greater than this PM or PM0. You can take it anyway, PE or PM or PM0. So what happens because of that? You know, acceleration will be equal to PM0 minus PE or PM minus PE. More the value of PE means what will be the answer? Your accelerating power will be negative. Negative accelerating power is nothing but what? It is nothing but it will go into a de-accelerating region or de-acceleration area. So therefore, now from this point onwards, your increased speed of rotor, that is omega, now it will start to reduce the speed and it will be slowed down. This speed will be what? It will be slowed down. Now what happens to the point E or here G? Let's say A, B, C, D. Now what happens to the point D? Here already we discussed after point D, whatever thing we discussed here earlier, it was in between point D to point E. But what happens at point E? So I can correct here. Here what you observe at point E, instead of saying or at point E, you can say in between. I will write it here. In between your point D and E. In between point D and E. Now what happens at point E? It is but obvious. Here PE will be equal to what? It will be Pmax 2 into sine delta 2. So therefore, due to the difference between PM and PE, speed reduces and delta will start reducing. Now we know that when the system is stable, now as far as equal area criteria is considered, when A2 will be equal to A1, then only the system is found to be stable. Now we have to discuss a very important point here: critical clearing time and critical clearing angle. The value of clearing time corresponding to clearing angle can be established only by a numerical integration. The equal area criteria gives only a qualitative answers to the system stability, as the time when the breaker should be opened is hard to establish. So what is your critical clearing time? The maximum allowable value at which circuit breaker operates. That is nothing but what? This is nothing but your critical clearing time. The maximum allowable value of time t is nothing but what? It is critical clearing time. And the maximum allowable value of load angle delta at which your system will be stable. So if it is your critical clearing angle, then before this critical clearing angle, system will be stable. After this critical clearing angle, system will be unstable. Now you people know what is the meaning of critical. Suppose I am giving a mathematics subject of university paper, and unfortunately I fail the subject. Now the one phase will reach, that is the subject will go in a critical situation. Means what? You have to clear that subject during that attempt only. If unfortunately you have not cleared the subject during that attempt, then it will go into what? You will be treated as a year down. And if you clear, then you will be safe, you will enter into a next class. So same analogy you can use it here. Critical is nothing but what? Before which, if your critical clearing angle delta, before which if you have a load angle, system will be stable obviously. And if your load angle delta is above this critical clearing angle, then system will be unstable. So please remember, the maximum value of a time which is allowed for a protective devices, that is a circuit breaker, to operate without loss of stability, it is treated as critical clearing time. So what is the significance of this critical clearing angle? If the question, somebody asks you question, what is the significance of critical clearing angle? So critical clearing angle gives information of stability of the system. If your load angle delta is less than the critical clearing angle, system will be stable. If the load angle delta is beyond the critical clearing angle, then the system will be unstable. And what is the significance of the critical clearing time? Now if you see, if I take a dotted line here, it will intersect to this swing curve, and if I take this dotted line here and if I extend this dotted line, then I will get this to this region. So this is nothing but, this point is nothing but your critical clearing time, that is TCR. So I think you understood what is the meaning of critical clearing angle and critical clearing time. For setting the timing of protective devices, this critical clearing time plays a very important role. Now this is the curve shown here only, up to this point only. But what will be the maximum value at which your area A2 will be? So see, this PM0, it will intersect to this curve at this point. So what will be your maximum area A2? So here it is drawn. This maximum area A2, it is drawn here. This is what is your maximum value of load angle delta, which is treated as a delta max. And already in earlier videos we discussed what is the significance of load angle delta, maximum load angle delta. Now here what you observe, if your area A2 is greater than or equal to area A1, then system will be stable. And if your area A1 is greater than A2, then system will be treated as unstable. This case we already discussed in a derivation of equal area criteria. I discussed this earlier. If you take a dotted line here up to this curve, and if you take a dotted line here, then whatever the point you will get on the time axis, this is nothing but your critical clearing time, that is TCR. Now from the diagram whatever we have drawn here, can I find it out value of delta max? Yes. This is your 0. This maximum point is nothing but a pi. Now how to find it out, the value of delta max? Delta max will be equal to what? Pi minus, now something will be there. Now how to find it out, that something angle? Please see, this line when it intersect at your curve, you will get here delta max. So please go here at this side. What you will get here, you will get some point where again it intersect initially. That angle is nothing but what? Your delta 0. So therefore how you can write, what is the formula of delta max? If you see, it is pi minus delta 0. Please see it carefully. This distance and this distance, it is same. Okay. So from the total pi, if I minus this distance, means same as that of this distance, which is delta 0, then you will get answer for a maximum load angle delta max. Now we know PM equal to PE equal to P max into sine delta 0. Where you will obtain this? At point A. At point A. Now how we can write the equation for area A1? Area A1 is the accelerating area. So I can write this as, what are the limits? Delta 0 to delta CR. So delta 0 to delta CR. Now what is upper limit for this? Upper limit is nothing but PM0. What is lower limit? Basically lower limit is nothing but PE, but if you observe, because of the fault this PE will be equal to 0. So what is your area A1? We can write it as integration delta 0 to delta CR into bracket PM0, or simply you can write PM, because here PE will be equal to 0 as there is a fault at point X. And how you find it out? Area of the A2 equation. Now here we have solved this. So if you put the upper limit, it will be delta CR minus delta 0. Mark this equation as equation number 2. Mark this load angle delta maximum equation as equation number 1. Now how you will be able to find it out? Area A2. If you see what is the upper portion of the curve, it is nothing but your PE. What is lower portion of the curve? PM0. So can I write it like this? A2 will be equal to, now you will take a limit from delta CR to delta max, then upper limit is PE, lower limit is PM. What is PE? P equal to P max sin delta, so it is written here P max sin delta minus PM. Now you know what is the integration of sine. What is the integration of sine? Yes, integration of sine is nothing but minus cos. Integration of sine, let's say delta, equal to minus cos delta. So we will put the upper limit P max minus cos delta max plus cos delta CR minus PM into bracket delta max minus delta CR. Treat this as your equation number 3. Now we know that for a system to be stable, what is the condition? Your area A2 should be equal to A1. So please equate this equation 2 and 3. If we have equated left hand side, now equate right hand side. So what you will get? PM delta CR minus delta 0 we have written, and this term here we have written to the right hand side. Now what I will do? I will rearrange the equation in such a way that we will have a P max cos delta CR on left hand side and rest of the terms will be to the right hand side. So rearrange this equation. So after rearranging, if you write a formula for cos delta CR, then you will get this formula. Here I have written all the steps. You can read it and you can understand it. It is self-explanatory. So cos delta CR equal to what? PM upon P max, delta max minus delta E0 plus cos delta max. Remember, this is very important equation. This is, what is this delta CR? This is your critical clearing angle. This is your critical clearing angle. Now can we substitute the value of delta max? Yes, we have a formula of delta max. Initially we have written that delta max equal to pi minus delta 0. This was your equation number 1. So I am going to put it here. So what I will get? Cos delta CR equal to PM upon P max. Delta max is nothing but pi minus delta 0 plus cos of pi minus delta 0. Now you know that what is the formula? Cos of pi minus theta. What is the formula of cos of pi minus theta? It is minus cos theta. So that's why to this term we have written this cos delta E0. Rest of the thing is as it is. Pi minus this will be 2 delta E0. So I can again write the formula for delta CR. So what is the formula for delta CR here? Cos inverse PM upon P max pi minus 2 delta E0 minus cos delta E0. This is your equation number 5. But already we have studied what is your PM equal to P equal to P max sin delta 0, where you will get it at point A in the graph. So can I write from this? Can I write from this PM divided by this P max? You will get here sin delta 0. Yes, we can write. So to this PM upon P max, I will put this sin delta 0. So I will get, if I substitute this, what I will get is delta CR as it is equal to cos inverse. In place of PM upon P max, we will get cos inverse. We will get sin of delta 0. The remaining term as it is, pi minus 2 delta 0 minus cos of delta 0. Treat this as a equation number 6. Now we know what is the swing equation. What is the swing equation? It is m d square upon delta E upon dt square will be equal to what? PM minus PE, or I will write it as a PE. And you know what is m? M equal to GH upon pi f or H upon pi f. So I can write it as d square delta E upon dt square will be equal to what? Pi f upon H, because I have shifted this m to this side. So it will be pi f by h. And what is your PA? PA will be equal to PM minus PE. The same equation here we have written. But we know here, as there is a fault at point x, this PA will be equal to what? This will be equal to 0. So we will write only this equation. D square delta E upon dt square equal to pi f upon h PM. Now integrate twice to this equation. Why we are integrating? And here integrating with respect to time, because now we have to find it out relationship or the formula for a critical clearing time. So if we integrate, what you will get? It is very simple. D delta E equal to pi f upon h PM t square. This is some constant of proportionality we will take, and it is nothing but delta E0. Now what I will do? Add delta E equal to delta CR. What is your formula of T? T will be equal to what? TCR. So in place of delta E, I will put delta CR, and in place of T, I will put TCR. So you will get this equation number 7 as delta CR equal to pi f upon h PM T square CR plus delta E0, where this TCR is nothing but critical clearing time. This delta CR is nothing but critical clearing angle. So if we rearrange this equation for the term TCR, then we will get this formula. Please remember, this is very important formula, and we are going to solve few numericals based on this formula also. TCR equal to square root of 2h delta CR minus delta 0 upon pi f into PM. This deviation of delta CR and TCR is only applicable in case as a during faulted condition, that is PE equal to 0. This is not used in other cases, in most of the cases. Okay. So here what condition we have taken? Here we have taken effect of the fault clearing time. Here we have considered fault at this point, that is point X, or on the other hand we can say fault is there on this bus, that is bus bar 1. This is very easy concept. If you have any doubt, please feel free to ask the questions. Subscribe my channel. Thank you for watching this video.